All right, guys, we're going to get started. So we've got the power department here today. They're going to show us a little bit about electrical hazards around the city and how to identify what power lines are hot and things to avoid. So we're going to talk to them, or they're going to talk to us first, and then we'll go over some medical stuff on the medical side when they're done. So I'll turn it over to you.
Well, thanks for having us out. My name's Brent Thomas. I'm the assistant director at the power department, and maybe just a little background. I've been with the power department for 32 years. Started out as a lineman, worked through, and now the assistant director. I brought Bart Miller with me. He's our engineering manager, kind of a similar path to where he's at. So we've been around and seen a few things, watched the city grow and the challenges that have come with it. I wanted to start off a little bit with kind of where the power comes from and a little bit of an overview of what we deal with in the city. Lehi City owns their own power company, and so anything that's in Lehi city limits is served by Lehi Power. There are some places where Rocky Mountain Power crosses through that were kind of some legacy customers that have been there for a long time. And so you will run into places where we have to deal with Rocky Mountain Power through the city. But the power starts, and we have one generation plant in our city, and it's actually by our offices in the back. This first slide is actually a picture of our generators. So we have 8 natural gas generators that are in this building, and they produce a total of 22 megawatts. So these are basically CAT reciprocating engines. So they would be, in most cases, they would run off diesel fuel. What we have are natural gas. They're 20-cylinder engines. There are 6 of them that are 20-cylinder engines, and then we have 2 that are larger that are 16-cylinder engines. So this is where it begins, and it's the same with generation facilities all throughout the state. Our particular facility, we generate at 12,470 volts. There are other facilities that generate differently, and then from the generation, it actually goes to a substation, which this is up by the flight park. It's one of our substations. And then it's brought in on the transmission lines that you can see, these tall poles right here. In our area, Pacific Corp is the transmission provider. And so we wheel it across Pacific Corp's transmission lines, then it comes to the substation, and it comes into the substation at 138,000 volts. And then at the substation, we step it back down to 12.4 and distribute it throughout the city. This is just a kind of a quick overview of the city. The different colors represent different circuits that are throughout the city. We have 8 different substations and 53 different circuits that feed all of the customers in Lehi City. And right now we serve about 33,000 customers with electricity. So it kind of gives you an idea of where our service territory is and the places that we serve in Lehi. So once it leaves the substation, it'll either leave on an overhead line like this one, or it will leave on an underground circuit that is probably more common. Like everything that you have around this area is underground, except for the transmission lines that cross through your property right behind.
Is there a time frame when you start to do that from power lines to underground?
Say that one more time.
Time frame, like what is the year they started to do that? They change more?
As far as moving them from overhead to underground, everything that's new, we do underground for the most part, but we don't really plan on burying everything. There are some advantages to leaving it up, and there's advantages to putting it in the ground. Obviously, power lines that are overhead are much cheaper, and they're easier to troubleshoot. Underground is less susceptible to weather and issues like that, but it's more expensive and it's a little harder to get done, getting right-of-ways and easements, things like that. So there's not really a plan to convert everything to underground, but our city ordinance says anything in a new development needs to be underground unless we have a really good reason why we don't. So So on this picture right here, it kind of gives you a little bit of a view of just a typical overhead pole. You've got the cross arm on the top, the 3 conductors on the top, and then as you move down, you can see the device that's just below the cross arm. That's a fuse disconnect. And then below that, the gray can, that's an overhead transformer. And then the conductors below, that is the neutral, and then there's a communication line just below that. This is just another example of that, just the crew setting a new pole, but it gets a little more complex with, multiple circuits coming into it, but still the communications down below that. Similar thing, this one has an underground riser, so when we're going from overhead to underground, you can see the gray conduit going down the side of the pole, and that's the underground conductor that's going down the pole through it to a subdivision. Okay, so just kind of some of the common things you're going to see out as you're driving through neighborhoods. We call it a sectionalizer. So this is basically just a junction box for high voltage cable. This is obviously when the box is closed, and this is what it looks like when it's opened up. So you've got primary high voltage cable that's coming in and out, and this is a 3-phase box, and so you'll see that there's 3 separate points of attachment there, and then you can attach multiple phases to each one. So that's kind of what you're going to see on the inside of that box. This is a switch gear. Looked really similar on the inside. The difference is we can actually open and close a circuit, and then the compartment that you're looking at right there behind those cables are actually fuses in those. So it's a place to fuse protect and to isolate circuits as we move through. So this is a 3-phase transformer. You'll see these on every commercial building. Your building here has one. This is the secondary side of the transformer, so it comes in at 12,000 volts, depending on the need of the customer. On this side, after it goes through the transformer, it's stepped down to 480, 208, 120, whatever the customer needs are. And so that's on the other side of the transformer. This is just a basic residential transformer. This one's single phase. On the next slide, you can kind of see what's going on inside of them. This is actually one that the primary connection, the elbow that you can see kind of going off to the left, hanging outside the box, actually burned up. And so you can kind of see it's charred inside. It's a little bit black, but same principle. If the case ground is broke on these, if it actually comes off of that, then this can be energized to 7,200 volts. And so the hazard on these is being, a vehicle contacting them and things being pushed off the pad or something of that nature. So those are kind of the the common pieces of equipment that you'll see throughout the city outside of the substations. This next one is actually an apartment complex, and so you can see multiple banks of meters, and then the boxes in the center that's blank with the black square in the center of it. That is the main disconnect for that section of that apartment building. So you're gonna run into this quite a bit, like down by the tech apartments, the new sanctuary apartments that are going in up by Young Living. This is a pretty common thing that you'll have multiple transformers feeding or multiple main breakers feeding an apartment complex. One of the things that we do try to do, more than try, we pretty much require it. If there is a physical separation in the building, a breezeway, a firewall, something like that, that's where we try to separate a section of it is being served by one particular main breaker and not have them cross through. So if you pull up on, like, say, down to the tech apartments, usually the transformer and the meters and the main disconnect are all there together. If you disconnect that, it should disconnect everything that is right in front of you that's going that way.
So this would be just the one big gray box. We could just turn the main off. We don't have to pull any breakers on this?
No, you would shut the main off. You don't want to pull the meters on these. You just want to shut the main off. And all the meters should go dark to the one.
On the residential, the same thing as pulling the meters, not de-energizing the house, right?
The meter base itself, it will de-energize the house, but the meter socket is still energized. That's the hazard on that. And I'll show you that here in just a second, but if you actually just walked up and pulled that meter, the jaws, the connections inside of that meter base are still energized. The house might be dead, and depending on what's on and what's functioning in the house, when you pull that, you could actually cause an arc in the meter base. So whenever possible, it's always best to turn off the main breaker, and then if need be, pull the meter. But so this is kind of a common one that you'll see on multifamily. There's several of these through the exchange over here, but they're not to this extent. They're usually smaller number of meters. This is what's inside of that CT can that we talked about. The CTs actually mount between these two bolted connections. So that one just kind of shows you what's inside that. This next one kind of gives you, this was an accident that happened on Main Street, kind of give you an idea of what we were talking about with the wires being broke. So the vehicle went through the fence on Main Street. This is kind of down by, used to be Scatty's. I can't remember what it's called now, but yeah. All about, yeah. And that is one of those primary junction boxes that the car ran over. So you can see everything has been tore off, and the ground wire, the neutrals have all been pulled apart. In this particular case, you really have no idea what's energized and what's not. Until we can get there and test it, you don't want to touch anything, you don't want to be around it, just keep people away from it. One of the principles that we work off, if it's not grounded, it's not dead. And so if you roll up on overhead lines that are down or something like this, and you think, well, all the lights are off around me, that there's a chance that it's dead, but these underground conductors are actually a capacitor, and so they actually hold a capacitive charge. And so even if the circuit is de-energized, there's a chance that you could get electrocuted off of that dead cable because it holds that capacitive charge. So it's just keep people away and wait till we can get there and actually ground it and make it safe. This one is actually a switch, but it kind of gives you an example of the copper wires across the bottom right here. That's the piece that was connected to the switch. And so when that gets pulled off, that green can, the metal part of that, could be energized. So got to be really careful with that. Okay, so that's the end of that. What I wanted to do is show you, if I can, a few different pieces of conductor and things that we use. So the thing that is really hard in identifying what is energized and what's not when you get out in the field on an accident or something, that is a piece of fiber. So it's fiber optic cable, and that is a piece of secondary cable that we run to a home. The black conductors on this are actually insulated, but this runs at 120 or 240 depending on where you make contact on that. So it's low voltage, but still enough to kill you and be an issue. Identifying the difference between that and that is not easy, right? And you kind of run into the same thing depending on the size of the conductor. With this is coax, so cable TV. This is one of the smaller house drops, but usually you'll see coaxes that kind of silver, a little bit larger conductor. But even with coax and with phone cables, they do have a low voltage that runs on them. So there is a potential for an electrical hazard there, not quite as much as what you have on a power line, but there is that potential there to have an issue. So you got to be careful with that. So it's really difficult to identify, these two conductors actually do the exact same thing. So this is overhead primary. This is copper that's been out in the field for a long time. It's kind of oxidized, and this is aluminum underground cable. And you can kind of see the center right here. That is the actual conductor. The pink stuff around the outside is insulation, and then you can see the copper wires around that. That is the neutral. That is the return path. And we can kind of pass these around if you guys want to look at that. But the hazard is actually the exact same. It's just whether it's under your feet or up in the air. These two are the exact same thing. This one just goes in conduit under the ground. This one goes up in the air. This silver conductor that is not insulated, that's the neutral. On this one, the one with the yellow stripe is the neutral. Those are the challenges that you run into especially with overhead lines that come down. If the neutral conductor is broken, the supply side of that comes energized at 7,200 volts. So a neutral is a current carrying conductor that always has the return path going back to the substation, but it doesn't have voltage on it unless it's broke. And so if you roll up on a vehicle accident and there's lines laying on the ground, there's really not a good way for you to identify whether that's the source or whether that's the return path. And if you happen to grab the wrong one, you're electrocuted. If you get lucky and get the right side, you may be able to drag it off the side of the road and be okay. So the best thing that I can tell you is if you roll up on lines on the ground, you gotta wait for us to come. That's really the only safe way to deal with this, because the other thing that you run into, like with a fiber optics cable, with the fiber optics cable, obviously it's glass, it doesn't conduct electricity, but some of it does have an armor shield around it, which is just a metallic tape shield around it. If that happened to get flipped up on the power line, if it was on an underground, a contractor digs it up, they can actually get pulled into the power line. I think you guys responded to a house fire that we had up by the cemetery a few years ago, where the contractors that were installing the fiber actually, at the same time, just bad luck, actually hit a phone line and our power line, and it pulled everything together, and it energized the phone line in the house and started the side of the house on fire. And so there's just not a good way to tell until you actually test it and see that it's dead and grounded. That's the only safe way to handle anything, whether it's power line or communications, because there's so many variables in it that there's no way to tell you. Yeah, if you see a silver coax laying on the ground, it's probably safe to grab. You just can't tell you that. The chances are it probably is, but if it were me, I wouldn't take that risk. One of the things that when we are working on anything, whether it's power line or communications, we use high voltage rubber gloves, and that's what we use to kind of start the process, to clean things up, and then start identifying whether we're testing to see if it's energized or not energized. The other thing that we use is fiberglass hot sticks. So that's just an example of one. We use that to open a fuse disconnect on a pole. So a fiberglass hot stick, the ones that we have are rated for 100,000 volts per foot. So that's why you can actually make contact with anything that's energized with those and be safe. And the reason that most of them are at the voltage that we're operating at, the reason that they're 8 foot long is that gives us that safe distance. If there's a flash, kind of stay out of that.
Brett mentioned that everything's energized until it's grounded. That will have a meter on it first, foremost, before anybody touches it. And that with that stick, that's how we'll test it with the meter on the end.
What's the like your on-call staffing overnight?
So that is one of the challenges that we have. We do not have a full-time dispatcher that is in the office. We do have a full-time dispatcher that they actually are unknown. And so when you call our outage number, you'll actually get that dispatcher, and then they can send the crews out. Our crews are available 24/7 anytime you need. The times that it gets to be a challenge is if, like Brian was saying, if there's a large storm and we're all over the place just like you guys and trying to get where you're at. But typically, if you've got something that's a hazard that you guys are waiting on, we try to get there first and get that taken care of. So, but there's the dispatch number, but there's also, if you guys would like, we've done this with the county dispatch where we have given multiple different phone numbers that is actually that you can contact directly if you need that, so we can help get crews there. So we could make those numbers available to anybody that wants those. I don't know why we kind of have a problem with Utah County Dispatch, that we've done it multiple times and they never seem to have a number when there's a problem. So I'm not sure what's going on there. But
We do.
so, but yeah, if, we would definitely, we want to make those numbers available to whoever needs them so that you can call. So we can pass this around too, but this is the backside of, like most of those meters that we showed. This is all they look like on the backside. These are the connections that actually makes it so it makes the connection for the power, and then it meters through the internal the processor inside of these. But when I talked about when you pull the meter off, the jaw is still hot. So typically you have one side that's the supply side, and then you have the other side that's the load side. We usually come in on the top and then come out on the bottom like that. So if you push this in, it makes that connection. When you pull that back out, the jaws that are the other side of these contacts, they're still hot. And so if somebody were to, brush up against it, put their hand in it, the electrocution hazard is still there. And so it's important. We typically would prefer that you don't pull these unless you absolutely have to, just for that reason. And they're not meant to, when you pull this off, it's actually not meant to break load. So there are switches and contacts that are meant to break load, and then there are others that are meant to, you have to de-energize it with the breaker and then pull it off. And that's what these are. You want to disconnect it with the breaker, then you pull this off. And so that's another hazard that you face on a house fire, is the socket that this actually goes into. So you want to be careful with that. And we can, if you're interested, we can pass that around. And also, some of the things that we've had with those is over time with UV and just being out in the field for years and years, they can get brittle. We've had the plastic in the jaws behind that's in the meter base that can get brittle. And so we've had them where you pull the meter off and you actually pull the jaws out with it and short circuit onto the can of the meter base. So there's a lot of hazard with that. That's why you prefer to shut it off first and then operate it so that you don't expose yourself to more than you should. One thing that you run into with electricity is there's a thing called Ohm's law, and so it's basically, it just gives you the mathematical formula between the relationship between all of your units of electricity. So the lower the voltage, the higher the current. And so you would think on a home, it's got 12240, it's kind of low voltage, and you'd think that would be a safe location. That's probably one of your bigger hazards right there, because you have a lower voltage and the current is really high. So a lot of main breakers the minimum main breaker on homes is 100 amps. A lot of them go up, well, the largest we allow is a 400 amp. On a circuit coming from our substation, they run at 12,000 volts, but they're only 600 amp. Now the amount of energy there is substantially more, but this particular location where you're so close to the meter base and you have high current and low voltage, if you start that arc when you pull the meter off, you have a potential for a really large flash, for flash burns and electrical hazards that way. So meters are probably the largest number of injuries that happen in the electrical industry, because it's probably a lack of respect because it is low voltage, but it's also there is that high potential for hazard there. And so meters, that's where a lot of technicians get hurt, meters. The other thing that you run into with a 480 volt installation is the voltage is just high enough and it kind of hits that sweet spot, so to say, with the current and with the voltage that sometimes when an arc starts, it won't go out. Most of the time on other voltages, it will trip the breaker and it will open the circuit, but there's times on 480 that it won't. And so pumps, well houses, things like that can be a particular hazard that is more than other places. Something else to keep in mind, as we were looking through those slides and we show you the main breaker, things like that's where the source is disconnected for a building like this or for a home. For the circuits that go around town, for individual transformers, that place that it's disconnected, it happens in various locations. So the one slide that I showed you with the overhead transformer and I had the fuse disconnect hanging down, That's the disconnect point for an overhead transformer. So if you had conductor that was the triplex, the one that has 3 on it, like we had in the back there, that's coming off an overhead transformer, and we pull that fuse disconnect, that de-energizes that transformer. So all of the secondary conductor going to the home would be de-energized. If it's an underground, like the larger conductor, like some of these, there is a fuse disconnect in the switch boxes, but not the sectionalizers. Then the next place that there is a fuse disconnect is the breakers that is in the substation. So remotely, the only place that we have the ability to disconnect anything remotely through SCADA is at the substation. We don't have SCADA capabilities anywhere in the field. So all of these switches or transformers or the sectionalizing boxes, if you were to call up and you had a particularly bad hazard that needed to be, everything needed to be de-energized right now, we could open the circuit and kill that entire area. But as far as killing a particular building or a section of that, we have to be there in person to do that. And so finding that source and getting it, de-energized and taking care of that varies depending on the situation you're in and where you're at. So we do, to be able to de-energize a circuit from SCADA, again, we don't have people in our office, so there would be a response time for us to get in and do that, or to get to the substation and do that, if the breaker didn't open on its own. So and again, this kind of gets into all the variables of why we say if it's not grounded, it's not dead. Because a breaker in the substation actually has a relay, basically a little computer that operates that breaker. Inside that are thousands of settings that if you happen to have, say, a tree branch land on an overhead line, it's going to sense that fault and it's going to open. And then if the tree branch fell off, it's going to reclose after a period of time and re-energize that circuit. If the tree branch didn't fall off, it's still going to try to reclose that one time, but if it senses that short circuit on there, then it will open and stay open. But if that tree branch happened to fall off, you're going to have a momentary outage, and then it's going to re-energize, and that circuit's hot again. And so there are all those settings that are in play that, if you've seen a flash, if you've seen a tree branch fall on a line and things go dark, they're probably going to come back, and you might see another flash if that branch or whatever came in contact with the line is still there. So all of the circuits in Lehi, they do that. They have that reclose capability, and so you have that hazard that you have to deal with. If you had a vehicle run over a switch or a transformer and it's arcing, that's going to happen in that case a lot of times too, to where it may open and then it's going to come back again, because it's to try and eliminate a lot of nuisance outages from lines slapping together or tree branches or things like that. Every utility in the country has breakers that operate the same way. And so if you happen to walk up and just got lucky with the timing and the circuit opened and you grabbed it and then the circuit came back in, you're getting electrocuted. And so that's something that's going to happen with every circuit. One of the things that, as far as Lehi, and this is just company policy, some companies, if they have an outage and they haven't had a chance to patrol the line yet, they'll actually try it once to see if it'll hold. Just because of how kind of condensed we are here, we don't do that. So if our breakers have gone through that series of operations and locked out, we go and patrol the line before we energize anything back in. So if you happen to be on an accident and you're sitting there, kind of keeping everybody away, we will come by and we'll look for whatever the potential hazard is before we would energize anything back in. So, but that, if you're waiting for Rocky Mountain, there is a chance that they're going to re-energize that circuit once to see if the temporary fault has cleared. So again, another reason why you don't want to be in contact with anything. So there's a lot of those scenarios that you just don't know So honestly, the best solution is just keep everybody clear until we can get there and test it and ground it, and then you can do what you need to do. We had a situation up on 12th East by the water tank one time where a car hit a pole and the lines were laying down on the car, and the lady that was driving was unconscious, and everybody was there, fire and police, and they had the area blocked off, and we were getting ready to test the line. We thought that the circuit breaker had tripped, and we were getting ready to test it and ground it so we could get the pole off and get the lady out of the car. And I'm standing there getting the equipment out of the truck, and out of the side of my corner of my eye, I see somebody run past. It's her husband, and he ran up to the car and pulled the door open before anybody could stop him, and just luckily the circuit breaker had operated and the circuit was dead. So those hazards are there, and that's the only safe way to make sure is if it's grounded. Or if we come and identify that it's communications, then if it's a hazard, we'll cut it out of the way. If it's not, we'll just try to pull it off the side of the road so that comms can come and take care of it. Okay, anybody have any questions? Anything? That's kind of all I had as far as what we wanted to share, but we're happy to answer questions.
Do you guys service the county addresses around the city too, or?
If they're in Lehi city limits, some we do. Some they're still on Rocky Mountain Power. So, and usually, I don't know if that meter does on it, but usually on the meter it'll say either Lehi City or it'll say Rocky Mountain Power. Yeah, and so that's one way to identify it. Most of the poles are tagged, so you can also see if it says Lehi Power or if it says Pacific Corp on them.
Even if it says,
not a foolproof way, because sometimes they're not marked. But
even if it says Pacific Corp, should we still kick out Lehi Power regardless?
no.
No?
You mean as far as de-energizing the circuit?
If there's an issue with the power pole, some of those inconsistencies with some of the poles or whatnot, are you guys wanting to be called as well?
Oh, yes. Yes, and usually dispatch will call us anyway.
Yeah, that's what I figured.
Because if it's in Lehi city limits, that's kind of what we've asked them to do, is just call us.
Okay.
Yeah.
So how common is city power departments? Does every city have their own, or?
Probably half of the cities in Utah do. There are a lot that have their own power system. Yeah.
The biggest ones are St. George, Provo, Logan, Springville, Payson, Murray. I mean, there's a lot of them.
Yeah.
They all kind of run off that same, whether you've got the generators, natural gas, or what's common in Utah? Is that most common system setup, or do they use other ways of energy?
So it's kind of all across the board. So we're actually part of a cooperative called UAMPS, and that's where all of our generation comes through, except for the one plant that we have at our shop. So we get power from coal plants, from wind, from solar, from gas compressor station, hydro. All of that is generated back on the greater transmission system, and then we take it here and use it. So IPP, the coal plant down in Delta, we're part of that. The Hunter plant in Castledale, we're part of that. The hydro that's on Jordanelle, we're part of that. There's a gas plant just off the freeway in Springville, Payson, I guess, that we're part of that. There's a wind farm, two of them up in Wyoming and Idaho that we're part of, and there's a solar field up in, I forget the name of the town, but it's just on the Utah-Idaho border that we have part of that. So we have several different projects that we're co-owners in with different cities that we get electricity from, and then that's where it comes back on these transmission lines and to our substations, and then that's where we pick it up and take it. It is at the substation. So, yep.
Awesome. Thank you so much.
You're welcome. Okay, hopefully that helps.
Definitely. Thank you.
So solar stuff goes back into it too, like on a house, on a residential, and then it's like credits that they get.
As far as with for solar.
Yeah.
So what actually happens is on a solar installation, we actually have a net meter, and it basically just measures power both ways. And if you have a solar installation on your home, it's going to measure what you generated from that, and then there's actually two meters, and then the other meter measures what we supplied. And I'm trying to remember because they just changed the policy on that, but I think what they do is that one time a year they would actually give you the credit for what you produced. I don't think we have any installations in Lehi that have actually generated more than they use. So even though they have solar, they're still pulling off from our system.
Alrighty. So we're going to keep going here. Just quickly go over on our end some electrical hazards and burns and just our protocols and quick review on that. Shouldn't take too much time. We're going to cover hazards and scene size up, triaging patients and priorities there, your primary surveys or your initial assessment, burn depths and sizings, treatments, and our transport destination. So we'll just review that real quick, and then we will be all set. So to start, just like he was saying, hazards, assume all power lines are energized. The foot shuffle thing, seems kind of like it's a little bit old school. I've never heard of that, but probably safer to just stay away from it, it sounds like. Establishing. What's that?
Yeah, it's like
Oh, yeah, jumping, yeah, from fire one. Yeah. Yeah, so just make sure that we're establishing a good hot zone. You don't want the lady's husband running in and grabbing the car like he was saying and contact utilities. So triage and scene safety. Scene safety's first, obviously. Disconnecting the power source. I really liked that he was talking about pulling the meter doesn't necessarily de-energize that socket. That's something I didn't realize. Good to know. And then waiting to evacuate the patients from the hot zone until it is been cleared by the power department. If it's a burn outside of electricity, then obviously we're going to want to stop the burning process, whatever that means, whether it's chemicals, and we need to call Barney and Tiny Dancer, or if we need to remove them from a fire, whatever that means. So stop burning is important, obviously. Okay, so your initial assessment here. One of the things to be aware of is that if there is clothing or anything else melted into the skin of a burn patient, we don't want to pull that off. That's going to take tissue with it. So what you want to do is just cut around that clothing the best that you can and then transport. One big thing to realize with burns, and particularly with electric or lightning, high voltage, anything like that, is that when you're triaging a patient, normally in like a mass casualty, we ignore the blacks, right, or the obvious deaths, and go and treat the ones that are going to be able to survive. Well, with lightning and high voltage, you actually have a pretty good chance of survival, so we're not going to ignore those. We're going to go to the blacks first and treat them first, and then everything else kind of falls into line. There is a NIOSH study that I was researching, and it said that if you get CPR going within 4 minutes, and ACLS, like full, compression, everything's going, and shock within 8 minutes, your chances of survival, if there's no underlying medical conditions there, is above 90%. So very, very high. A lot of times that these patients are just going to be in VFib, and they respond really well to defibrillation. Okay, let's talk about burn depths. So there's 3 of them. First degree, who can tell me what a first degree burn is?
sunburn.
Sunburn, yeah. So red, painful, no blisters. Second degree, anybody?
Start to get blisters.
Yep, that's when it turns to you've got a few blisters. Other than that, same as first degree. Third degree?
Black, charred.
Black charred, yep. One of the things with third degree is it's going to, a lot of times, I don't know if this is necessarily something that is going to be 100% of the time, but some of the time their nerves are singed at that point, and so they don't have any pain, so lack of pain is another sign. I don't know if that's 100% of the time or not, but just something to be aware of. Yep. Okay, rule of nines. Who wants to be brave? Brielle wants to be brave. Can you remember the numbers for an adult? 9. Yeah.
For all but the groin area?
Yep, 9 for all but the groin area, and then the bigger ones get 2 9s or 18, right? Anybody remember for peds? That one's a little bit harder because it's rule of 9s, but not exactly 9s. So for the adults, Brielle was right. It's 9 for head and arms. It's 18 for the front of them, 18 for the back of them, 18 for each leg, and then 1 for the groin. For kids, since they have bigger heads, it's going to be 18 for the head, 9 for the arms, and then everything else, well, the front and back is the same, and then legs are 14, whatever reason they came up with that. And that's going to be important when we talk about our treatments. So a lot of people forget with sterile dressings when it comes to burns. One of the things that you want to be aware of is it needs to be the dry sterile dressings, because I know a lot of times in different types of injuries and traumas, we're going to use the moist sterile dressings. These ones need to be dry. And then spinal immobilization. That's going to be important because a lot of times this comes with like a secondary injury, whether it's, they were electrocuted and fell off a ladder or anything like that. So being aware of that. Removing items that can constrict swelling. So with any burn, regardless of how they got it, time is going to be of the essence because of that swelling. So, or airway. So it's going to be important to notice those signs and move quickly. So cutting off clothing before it gets to the point where you can't, or protecting their airway before it's completely closed off are super important. So time is of the essence. And then obviously pain and anxiety management, fluid resuscitation we already talked about. and then hypothermia. So at this point, your skin basically provides a lot of that temperature regulation in the body. So if you've burned off your skin, there's going to be issues there. So keeping that patient warm and monitoring that on the way to the hospital. Some special things with burns, circumferential burns, that's going to be when it goes all the way around one body part. So it can be your arms, your legs. One of the most important ones is anything that's going to restrict your breathing. So around your chest, neck, those are going to be particularly dangerous as far as severity and making it or protecting that airway quicker. Facial burns, obviously, same thing. If they've got anything burnt on their face, it's going to be a higher priority. Carbon monoxide poisoning is going to be something that comes along with burns generally, just because of the off-gassing or anything involved with that process. Hypothermia, we talked about. Compartment syndrome. Anybody know what compartment syndrome is? Remember that?
Where the fluid builds up like in your thigh or something.
Yeah. So
Swells up to big enough where it's like tension.
yeah. So Captain Evans was saying it's any time that your fluid builds up in a area of your body that causes pressure, which is correct. So basically, what it is your muscles and organs, everything is inside these little sacs called fascia, and if any one of those given fascia gets to the point where the swelling in that area is too much, it can cause compartment syndrome. That can basically it can cause permanent damage. So that's when they're going to start considering doing the escharotomies and stuff at the hospital. So not necessarily us. I think they used to kind of do that a little bit more in EMS, but gone away with that. And then rhabdo is another serious concern there. So that's going to be a little bit longer term, more of a hospital consideration, but yeah. Okay, so let's talk about transport decisions. There are a couple that are listed in our protocols where it is a no question you're going to a burn center, similar to the trauma triage protocols. And in fact, they reference that as well. But anytime that there's any inhalation injuries or suspected injuries, anytime there's a partial or full thickness burn that's going to be second or third degree, that's more than 20% of their body area in adults and 15 in pediatrics. Circumferential burns, and then partial or full thickness burns, regardless of size, in the face, hands, or genitalia. Make sure to consider calling an air ambulance, especially if you think that RSI is going to be needed to protect that airway. We obviously don't have those capabilities, so getting them coming is always going to be helpful. One thing to remember as well is if there is trauma involved in these burn patients, regardless of what mechanism it is, your priority is going to be taking them to the trauma center, not the burn center. So they'll want to stabilize those first. In Utah, we've got one option as far as definitive burn care. That's the U. So generally, any of these situations are going to head to the U. Okay. Any questions? Awesome. Thank you so much. Hopefully that was helpful.